is the reliability and safety session, and we will have 6 papers, and in particular, this one from the new idea and emerging result track, another one from source engineering in practice track, and we have some other paper from the technical track. Please remind that this session will be recorded, so I hope everything is fine with you. And as you know that we will start now with all the presentation, and you remind that you have 5 minutes per presentation, and after all the presentation we will have the discussion. So I encourage you to use some, we have some emoticon here, now that you can, because it's important to have some interaction during the presentation, this type of thing. So I will encourage you to use this. So I think we can start with the first paper, and the first paper is automating a staged rollout with reinforcement learning. Is from the new idea and emerging result track. Our speaker is Lanch Fiondella from University of Massachusetts. Please, Lanch. You have.
I'll just share my screen.
Please.
Okay. Could you confirm you can see my screen?
Yes, please.
And that it advances. We're on slide 2. Can you see slide 2?
Yes, please.
Okay, great. So just want to make sure that people are seeing what I'm showing. So thanks for coming to this session. I'm a little bit off the beaten path from many software engineering researchers. I'm a computer scientist by training. My research is in reliability engineering, so I do probabilistic and stochastic modeling, meaning that I am looking for colleagues who would like to collaborate, who like to do the experimental work, collect data, and want somebody who's both good at statistics and probability. But the topic that I'm interested in from that background is modern software practices generally. There's lots of talk about all these, it's all, generationally in software, there's all the word soup of buzzwords: DevOps, continuous integration, continuous deployment, site reliability engineering. And what, this work is aspiring to do is at least make a dent in the effort to provide more mathematically rigorous models that would enable people who utilize these practices and processes to measure and optimize. So you can't optimize unless you have a baseline, and therefore measurement is critical. The work is based on, there's a nice definition. So we tried to breathe life into this definition of DevOps from the text by Bass and some of his co-authors, that the notion of delivering high quality software while not compromising quality. And in that includes reliability, security, safety, and so on. So really we tried to deconstruct that definition and give it some kind of mathematical meaning. This is just one attempt, and certainly others and more detailed models are possible. But what we ultimately do is just make a simple model of the notion of this staged rollout process. It's seen in site reliability engineering. And what we show is that it gives natural rise to a trade-off between delivery time and downtime. I'll talk about that in the context of a simple model, which serves as the basis of a reinforcement learning algorithm, a Markov model. So, I don't need to preach to the choir. We all know we want high quality software, and I've only got 5 minutes. So like I said, we've developed this MDP, but it really was just traditional state-based modeling. We didn't do this with, reinforcement in line as an application. We just thought maybe we could do some more intelligent automation of these modern software practices. So here's the model. And the notion is that on the left, we could be in the development state or the ops state. The implication here is that either only developers or some number of users. The middle state denotes this notion of what I refer to as incremental deployment. But like I said, in the literature, it's referred to as staged rollout. This would be, obviously, Facebook doesn't just dump some new code onto millions and millions of users that could cause catastrophic outcomes. So the notion is that you might expose some subset of the user base to some new feature, and if it goes bad, at least it can get rolled back to the dev state. And so the idea here is that these lambda transitions represent failure rates. And when you have fewer users testing software, developers are talented at ferreting out the problems, but nothing can match the sheer stupidity of the overall user base of the software. They're going to, press buttons and sequences that the programmers just didn't think of. So the idea is that as we go from left to right, the failure rate will increase, meaning that we get, in the context of reliability engineering, this notion of accelerated life testing more generally, whether it be hardware, but in this case, software. What the decision problem that arises is, how long should we spend before we transition from the dev state to this stage rollout state? And then we can have simple time-based policies that say, well, if we just wait some number of units of test before we transition, then we're less likely to experience the inconvenience, the competing factor, which is downtime. So in other words, if everybody has the software and it's buggy, many people are going to be unhappy. Maybe it's causing code to crash on servers or whatever it is, or some other form of inconvenience. So downtime was just the trade-off, but you can see there's a natural compromise between trying to accelerate the discovery of the defects by pushing the code to a larger and larger user population, and the desire to prevent the users from having these undesirable outcomes. And Pasqualina, if you would please give me the 1 or 2 minute warning, I would appreciate it, because I haven't been keeping track of time. So please do that. Here, and please just do it verbally, because I won't see the chat. So here's the idea. We took traditional software reliability data. You can see that each vertical bar represents the time at which a failure occurred. This might not be the nature of failure data in a more modern software practice, but you can see that as time progresses, there are fewer failures because defects are being identified and repaired. So the notion is that we should probably be in the dev state where we can fix things, we can find things, but without causing inconvenience to the users. But in the later stages, maybe we want to be in that middle state or that right state. And then we went through this, defined for the sake, back of the envelope numbers. The population might be 10,000, the middle state might be 10% or 1,000, the developers could be 50. And then this is wrong, I know it, but just wanted to put something on the books. The ratio of the number of users in successive states could define the acceleration factor. So for example, if there is 1,000 over 50, we know the developers are better, but we could have a essentially faster, instead of being on wall clock time, we're on compute time. And then we define delivery time as getting to that last failure on that timeline, plus the time to go from the left to the right state. And similarly, the downtime we define as the state we were in when things failed. So we enumerated a combination.
Sorry for the interruption. Yeah, you pressed. I was making some sign. Please. If you can go ahead, because you had 5 minutes. I was doing right. Some sign to you. Please, not sure. Just to tell you.
No problem. Okay. I don't want. So here I am at the 5 minutes. I'll just show you the results. So we emulated a range of policies with a brute force method to just pick pairwise combinations of delivery transitions from the left to the middle state and the middle state to the right state. And then we used reinforcement learning. It didn't come out perfect, but it was able to identify policies that achieve trade-offs between delivery time and downtime. Hopefully we can improve that gap with future research.
Okay, great. Thanks a lot for the very interesting presentation. So now we can go to the second. I was telling you, we can start also to collect the question in the chat. So please use the chat. We can create some question queue. So if you want, that we will discuss at the end. So the second paper is an empirical study on quality issue of eBay Big Data SQL Analytic Platform. This paper is from Soft Engineering Pratic track, and we have the presenter is Feng Zhu. Please, Frank, you can.
Okay, let me share my screen. Can you see my slides?
Yes, please.
Okay, hello everyone. My name is Feng Zhu. I am a software engineer from eBay. Now let me make a brief introduction about our paper, an empirical study on quality issues of eBay's big data SQL analytic platforms. For enterprises, psychoanalytics platforms are important to decision support and business intelligence. With ever-increasing data volume, many organizations started to choose Hadoop's ecosystem as a big data solutions for scalability. Meanwhile, a number of new big data circle systems have been proposed and gained popularity, such as Apache Hive and Spark Circle. In eBay, we also started to build such project named Camel since 2018. It is based on a well-known Spark and follows a typical Circle and Hadoop architecture. In our production deployments, Camel provides services with many Swift servers running in Hadoop cluster. As a fundamental infrastructure of the company, the platform service quality can adversely affect the user experience and business. Despite the popularity of the open source-based big data circle systems, we found few studies on quality issues were carried out. According to our daily maintenance activity, we believe it is important to understand common issues of their root causes. Therefore, we studied 1,884 tracked issues and in Camel and tried to answer the 3 research questions. What are the common symptoms of the service quality issues? What are the common root causes of service quality issues? And what efforts researchers can do to mitigate these issues? For the first research question, we found the issues can be manifest as one of 15 main symptoms. The symptoms can be classified into 3 categories: job failure, job slowness, and wrong results. The most 2 prominent job failure symptoms are IO exceptions and threshold exceeded exceptions. As for the job slowness, one case is the abnormal non-running against the common sense. Another one is a relatively longer time than before. The wrong results can be incomplete data or incorrect values. In our practice, we found some wrong results may be identified even after several months since it happened. For the second research question, we found the root causes can be classified into 3 major categories. About 15% quality issues are caused by user-side faults. About 46% issues are caused by system internal defects in Camel Spark during query and planning execution phase, and nearly 14% caused by mismatches among different open source components in Hadoop ecosystem. The second research question is the core part of this paper, and we conduct in-depth analysis and discussions for them. For the third research question, we just want to highlight several pinpoints and lessons learned in our practice, including the lack of circle anti-pattern detector, effective plan transformation, automatic configuration, efficient data management, and advanced replay tools and diagnosis tools. To conclude, we perform study on the service quality issues of eBay's Camel platform in our practice. We present symptoms, identify the root causes, and further discuss lessons learned to motivate future research. Okay, thank you for listening.
Thanks a lot for the great presentation. We can proceed with the third paper, an heuristic for probabilistic reachability to identify hard-to-reach statement. This paper is from the technical track, and we have Samantha Sao from the University of California that will present the paper. Please.
Thank you. Hello, everyone. I'm Shimanta Saha from Verification Lab at University of California, Santa Barbara. I will be presenting our paper, Preach, a heuristic for probabilistic reachability analysis to identify hard-to-reach statements. We have developed an approach called Preach that can identify hard-to-reach statements. Given a program and a target statement, Preach identifies if the target statement in the program is easy to reach or hard to reach, considering that randomly inputs are generated to test the program. consider this program from software verification competition benchmark. There is an assertion statement in the program. Preach can answer questions like, is the assertion statement hard to reach for a random testing tool? Or to be more specific, Preach can compute what is the likelihood of reaching the assertion statement if we run a random testing tool. Existing techniques that can be used for probabilistic reachability analysis to identify if a target statement is easy to reach or hard to reach are probabilistic symbolic execution and statistical symbolic execution. But the issues with symbolic execution-based techniques are there can be exponential increase in the number of program paths, and linear increase in path constraint size can lead to exponential increase in cost of symbolic execution. And the complexity can increase further if you are trying to use a model counting constraint solver for probabilistic analysis. Whereas symbolic execution-based technique deals with path constraints, in Preach, it needs to deal with only branch constraints. As a result, the exponential analysis cost of symbolic execution can be reduced to polynomial time analysis cost. We developed the technique Preach that trades off accuracy for scalability. Given the program and the target statement, Preach first constructs a discrete type Markov chain. And using that Markov chain and a probabilistic model checking tool, Preach can compute reachability probability. Once it can compute the reachability probability, and given a threshold, it can identify if the target statement is easy to reach or hard to reach. Preach first extracts the control flow graph from the program and also identifies the target statement in the program as target node in the control flow graph. From the control flow graph, it does dependency analysis to identify which nodes in the control flow graph are dependent on the input. And then from the control flow graph, it constructs the discrete type Markov chain. Now the question here to ask how these probabilities in the Markov chain are computed. To compute the probability, we introduced a new concept called branch selectivity in this paper. Let's consider this program where input is the test input, and then we want to compute all this branch selectivity. Preach first extracts the branch condition. From the branch condition, it constructs a branch constraints in SMT leaf format. Then it makes query to model count and constraint solver. As a result, it has the model count or number of satisfying solution. Then dividing it by the domain size, it computes the selectivity. For example, the branch condition at line 2 has selectivity of 1 by 2 to the power 32. Then we see that branch selectivity computing based on only branch model counting is not enough because it cannot catch variable updates in the program. So we also used abstract interpretation to collect refinement conditions. And using branch model counting and abstract interpretation, we compute branch selectivity. And using that branch selectivity, we can compute the probability in the discrete type Markov chain. And once we have this discrete type Markov chain from the control flow graph, it converts it to a DTMC model accepted by probabilistic model checker tool Prism. We also construct a query, which is PCTL query. And this query asks questions like, what is the probability that target node in the discrete type Markov chain is reached eventually? Once we send it to the probabilistic model checking tool Prism, we can compute the reachability probability. We have implemented our technique for Java programs. There are 3 different versions of these tools. When you use simply model counting, it's Preach, and based on the refinement of branch selectivity based on abstract interpretation analysis, there are 2 other versions. We have evaluated Preach on software verification competition benchmarks and performed some case studies. This is publicly available, and you can also run using Docker. And our assessment on software verification competition benchmarks, we find that Preach is very accurate, precision, has high precision and recall. Then we compared Preach to existing probabilistic reachability analysis tool like probabilistic symbolic execution and statistical symbolic execution. We find that Preach has better precision accuracy compared to both probabilistic symbolic execution and statistical symbolic execution. Not only that, but we also find that Preach is orders of magnitude faster than this existing symbolic execution-based tool. We developed a technique that we show that can identify hard to reach statements in the program based on probabilistic reachability analysis. But this technique can be also used in future for probabilistic analysis of software and quantitative program analysis. It can be also used for guiding hybrid testing strategies or even improving random testing or fuzzing efficiency. That's all from my side. Thank you.
Great. Thanks a lot. Thanks a lot for your interesting presentation. Please use the emoticon for also encourage the presenters. So we have another paper, a study of unstable numerical method and their solution in deep learning. That is always from the technical track. We have Ilinska. That is our speaker. And introduce better yourself.
Thank you.
Please. Please.
My name is Ellie Cloverdance, and I'm currently a PhD candidate at Iowa State University and also a senior data scientist at K-Privacy. And I'm going to present deep stability, which is a study of unstable numerical methods and their solutions in deep learning. Numerical stability is a property of an algorithm that comes from the fact that mathematically equivalent algorithms can have very different numerical properties. And there are two types of numerical errors, round-off errors and truncation errors. Round-off errors arise due to representing real values only with finite precision, only with a finite number of bits. And truncation errors arise from performing only a finite number of iterations for an iterative algorithm. For instance, the derivative is a great example of that. Numerically unstable algorithms are very sensitive to these numerical errors, and they can lead to inaccurate or incorrect solutions. And in deep learning, we perform a lot of numerical computations in finite precision and iteratively, and therefore some deep learning algorithms are numerically unstable, which negatively impacts the reliability and safety of the software where they are used. The challenge of analyzing numerical stability of deep learning is that it requires interdisciplinary knowledge, including, but not limited to, software engineering, numerical analysis, and deep learning. And detecting and diagnosing numerical stability issues is difficult because those issues are often triggered by just a narrow range of inputs, and errors can occur silently and propagate through the neural network far from the origin of the problem. And also, the solutions to numerical instability are often very algorithm-specific and require algorithm-specific knowledge. I'd like to give a motivating example of softmax, a commonly used function in deep learning. And on the left side, that formula shows the definition of softmax. However, if we implement softmax exactly as per this definition, it is actually numerically unstable. And we can see the outputs that it gives when we implement softmax using this unstable definition, that it can output nan, not a number, for some relatively normal numbers. The solution to that is to rewrite the formula for softmax to make it more numerically stable. And the solution is shown in the formula on the right side. And what we do here is we subtract the maximum of x for each xi, and therefore normalize each xi. And we show that this implementation is reliable and outputs the correct results. So this motivating example demonstrates that mathematically equivalent algorithms, and we prove in our paper that these two are mathematically equivalent, can have very different numerical properties. So we ask 3 research questions, and to answer them, we leverage the commits in the PyTorch and TensorFlow repositories. First, we ask which deep learning algorithms are numerically unstable. And we find that it is typically operations within tensor maps, such as remainder, standard deviation, logarithm, exponential, as well as operations in statistical distributions, data processing, and neural network quantization. The second question investigates the cause and impact. And we find that the cause is typically overflow, loss of precision, and underflow, which lead to incorrect or inaccurate results. And the third question asks, what are the solutions to this? And we find that there are 4 primary solution patterns. First is rewriting mathematical formula, like we saw in the case of softmax, the motivating example. Second is increasing the precision or changing variable type. Third is using a different algorithm. And fourth is limiting the input range. In addition to answering those questions, we also discovered that these 4 algorithms are numerically unstable, and that has not been discussed in prior literature. And in conclusion, we make 5 primary contributions. We identify which deep learning algorithms are numerically unstable and explain why. In our paper, we show a lot more detail than this presentation, and we perform an in-depth analysis of the root cause and impact and provide both mathematical and code level solutions. We summarize all of our findings in a database we call Deep Stability, which is publicly available. And we envision that it can be used by deep learning developers to help to diagnose and fix issues. And we have actually used it ourselves to submit a pull request to TensorFlow to fix a numerical instability vulnerability. Thank you.
Great. Thanks a lot. Thanks a lot for very interesting presentation. So we can proceed with the next paper. If a human can see it, so should your system. Reliability requirement for machine vision component from the technical track. We have Bowie Caroline Wu from the University of Toronto. Please.
Thank you very much. Hello, everyone. My name is Caroline. I'm from the University of Toronto in Canada. Today, I'm presenting our work in collaboration with University of Waterloo, titled If a Human Can See It, So Should Your System, Reliability Requirements for Machine Vision Components. So machine vision components, MVCs, are currently deployed in safety critical systems, such as autonomous driving cars and medical imaging devices, where undesired behaviors can lead to fatal accidents. For example, the MVC in the Uber case failed to recognize a pedestrian and led to a crash. Such vision tasks are hard to specify. Therefore, they're normally performed using ML. However, in order to check correctness prior to deployment, one still needs to define what it means for an MVC to be correct. In this work, we focus on one specifiable safety property, reliability against environment changes, such as the dark light in the Uber accident. This is commonly known as ML robustness. However, since dark is not an invalid input or stressful condition studied by robustness, but a necessary normal deployment scenario. Therefore, in this paper, we refer to this property as reliability. In software engineering, reliability is the ability of a system or component to perform its required functions in a specified environment and a specified period of time. So in this paper, we consider reliability of MVCs as whether the performance of an MVC remains reliably unaffected by image transformations that commonly occur in real-world scenarios. Since MVCs are developed to automate human vision, in this paper, we use human performance as a baseline to define reliability of MVCs against realistic changes in the real-world deployment. More specifically, if the changes do not affect humans, they should not affect MVC either. To this end, we specify 2 reliability requirement classes for MVCs with parameters representing human performance, a correctness preservation and a prediction preservation. Also a method to instantiate them into machine verifiable requirements and a method to check MVC satisfaction. As an example, consider the reliability of image classification MVCs against the transformation artificial frost addition, which is shown in the images on this slide. The instantiated correctness preservation requirement states if the recognition accuracy of an MVC should not decrease if the visual change in the image is within the range delta V less than or equal to 0.84. And the instantiated prediction preservation states the percentage of labels an MVC can preserve after adding frost should not decrease if the visual change in the image is within the range delta V less than or equal to 0.91. In both requirements, delta V is our defined metric for measuring visual change in images, and the numbers 0.84 and 0.91 are estimated using human performance data. They represent the range of how much visual change does not affect human performance, which is a human tolerated range. Intuitively, in the 4 images shown here, the car is clearly visible for humans in the first 3 images. They are within the range we consider. And the last one, the car is no longer visible, therefore it's outside of the range that we consider. Okay. Neither of our requirements subsume the other. Correctness preservation checks for the correctness of decisions, and prediction preservation checks for the preservation of decisions. And correctness preservation requires ground truth, whereas prediction preservation can be checked on unlabeled images. If an MEC satisfies only correctness preservation, it may correctly recognize different objects before and after a transformation. If only prediction preservation is satisfied, the MEC might preserve incorrect decisions and change the correct ones. If both are satisfied, then the MEC is both correctness and prediction preserving, which is ideal. If neither is satisfied, then the MEC is neither correctness nor prediction preserving, which is undesirable. As evaluation, we first evaluated our range considered in our requirements by answering how well do existing reliability evaluation methods cover the human tolerated range of changes. We showed that the state-of-the-art benchmark datasets for checking MEC reliability do not address this range. We then are interested in how effective is our requirement checking method in identifying reliability gaps compared to existing approaches. And we discovered that by checking the satisfaction of our requirement, we can detect reliability gaps missed by state-of-the-art benchmark datasets. Therefore, we conclude that it is useful to check reliability using our requirements. Thank you very much.
Great. Thank you very much. Thank you. Very interesting presentation. So we will have the last presentation, a neural method for test oracle generation, that is always from the technical track. We have Gabriel Rian from the Columbia University. Please, Gabriel.
Okay.
Please.
Can everyone see my screen?
Yeah,
and hear me?
Please,
Okay,
please.
thank you.
Go.
Okay, yes. Hi, everyone. I'm Gabriel Ryan, and I'll be presenting Toga, a neural method for test oracle generation. So in automated testing, the test generation process can be broken down into two tasks. First, generating the test prefix, which executes the method under test. And second, generating a test oracle, which describes the expected behavior and determines if the test passes or fails. So in Toga, we focus on the test oracle generation. And in general, this is a hard problem because it's difficult for an automated method to know what the expected behavior should be. So for example, when you're testing a stack, we know that a stack that calls push and then pop should be empty afterwards, but a automated testing system would not necessarily have this understanding. So people have used a few different approaches to address this problem. First of all, what we call safety oracles enforce general safety properties on the program under test. So an example of this would be saying that a method should not throw a null pointer exception on a non-null input. And these are generally good for finding certain classes of bugs, but they can't check for program-specific properties like a stack being empty. So to check for program-specific properties, specification inference methods mine user-written docstrings to generate test oracles. And these work well when the docstring is present and well-formed, but if a docstring is missing or malformed, then they're unable to generate an oracle. More recently, neural assertion generation methods use a neural network to generate the oracle. And these are more robust to missing or malformed docstrings, but they don't provide any syntactic guarantees. So often they'll generate oracles that look correct, but they may actually fail to compile. So in Toga, our objective is to utilize the robustness and flexibility of neural networks, but also provide compile and runtime guarantees. And in general, we do this by leveraging the observed structure of oracles. So even though the set of all possible oracles is massive, and there are a lot of invalid oracles in that set, in practice, if you look at developer-written oracles, they actually follow a small set of common structures. And so we can leverage these structures to restrict the space that the model has to search over and make the model's task much easier. So we express these structures using a simple grammar. And this grammar incorporates both exception oracles, so whether or not an exception is expected by the test, and also assertion oracles based on the type of variable in the assertion. And we deliberately make this grammar very restricted, but we find that it still fits most of the tests in a developer-written corpus. So Toga works by taking the test prefix and method context as input, and then running two models. First, an exception oracle classifier, which predicts whether an exception is expected or not in the test. And second, an assertion oracle ranking model, which selects an assertion to use for the test oracle if an exception is not expected. So the assertion inference works by first generating a set of assertion candidates from our grammar, and then using the model to score each one of the assertion candidates based on the method docstring and test prefix. And then we take the highest scoring assertion and use that as the test oracle. So overall, we integrate Toga with an automated testing tool which provides test prefixes, and we combine those with the Toga-generated oracles to generate complete unit tests, which we use in our evaluation. So for evaluation, I'll just go over 2 key points. First of all, we evaluate Toga for assertion inference accuracy on Atlas, a benchmark of assertions published in ICSE 2020. And on this benchmark, Toga achieves 69% accuracy, while our baseline model, which is a pre-trained sequence-to-sequence transformer, achieves 62% accuracy. And to the best of our knowledge, this is the best result so far on this benchmark. Second, we evaluate Toga on defects for J, which is a benchmark of real-world bugs from large Java programs. And on defects for J, Toga finds 57 bugs, while the next best performing method in our evaluation, Randup, which is a randomized safety test generator, finds 20 bugs. And in particular, Toga is able to find these bugs because it is testing for program-specific properties using both exceptions and assertions, while Randup is testing for safety properties only. So it is finding bugs based only on unexpected exceptions that get thrown. So finally, thank you for listening, and I'm happy to answer any questions in the Q&A session.
Great. Thank you very much. Thank you very much, Gabriel. Okay, thanks a lot for all the presentation. So we can with the session, with the discussion session. So I see one question in the chat. So we can start if you want from the question that is in the chat. So I don't know if the person that posted the question want to ask directly the question. You can now mute yourself, Melzini. I think it's the question is for Elinska. Otherwise, I can ask, so we can. Okay, you need some time. Maybe we can start with another. If you have another question for Eliska, okay, is arrived. Okay, please.
Yeah, thank you. I just unmute myself. So I have a question about the deep scalability, and I find from your presentation that you can identify some new instability in DL algorithms. So can you explain more? How did you identify these issues? Have you used some heuristic ideas or some rules to detect these algorithms? Thank you.
Yeah, for sure. So what we did was we actually searched PyTorch and TensorFlow repositories for certain keywords that would relate to numerical instability or like the symptoms of numerical instability or fixes. And then we went through this entire list and reviewed it manually one by one to filter out the ones that were not relevant. And then for the ones, for the commits that actually did relate to numerical instability, we analyzed it in great depth and reviewed exactly, what was the issue, what was the cause, what was the fix, etc. And then for each of those, we record that in our database. So it was basically manual effort. But now that we have this database, we can extract some patterns to use as heuristics that can be used, in the future to, for instance, build a tool that will do this detection a little bit more automatically. But essentially, our work was based on doing an in-depth analysis of each individual issue. And then by doing that, we found some issues, for instance, cosine similarity algorithm being numerically unstable. And we did not find any mentions of that in prior literature. So by doing that, we were able to discover some algorithms that were numerically unstable, but not discussed before as numerically unstable. Does that answer your question?
Yeah, thank you. Thank you. It's very clear. Thank you.
Thank you.
Okay, great. So we can proceed if you agree. So we can start we can ask a question to Lance. If anyone has any question for the first paper, automatic stage rollout with reinforcement learning. So to give the opportunity to all the speaker to have
And if not, that's okay too.
But I can ask you one question. So regarding the applicability of your work, no, I think it's very interesting work, and you have this DevOps. So can you better let us know more about this for the applicability of the work? So, and also how do you, if you have any plan for the next step?
Right. So, I mean, I don't know if I can answer that entirely satisfactorily myself, but I will say that, that was a simple state model. There were 3 states. There were 2 transitions from left to right. It could be that simply, we can think of that as a simple time-based policy. Obviously, just because you didn't fail doesn't mean your software is reliable. And so it could be that, maybe some kind of vector of test activities and the time spent doing those tests would be the way in which we have a better way of judging if, okay, we've done this much testing, either reliability or security, and seems okay, so maybe it's okay to go to this next stage of the state model. Things like that. That's what we're planning on doing going forward.
Mm-hmm. Okay, great. Thanks a lot. And I don't know if we can proceed, if you agree with a question for Feng. So that was from the Software Engineering in Practice. So the paper, an empirical study on quality issue of eBay Big Data SQL Analytic Platform. If you have any question for Feng. Otherwise, I can also ask a question. So I think it's very interesting experience that you reported, because so how do you, I like it when you've written that our thing is not only facilitates engineering to diagnose and fix the issue, but also motivate an automatic tool for the ease of manual maintenance. So can you elaborate more on that? So for the how to exploit your the result that you had.
From the root causes, we found many research opportunities to improve the reliability and performance. We found several. We summarized our Nelson's pain points and insights from the future research questions. To begin with, it is the circle anti-pattern detector. The lack of circle anti-pattern detector in big data ecosystem. In the traditional relational database areas, the SQL anti-pattern detector tools, it is common, but in the Hadoop ecosystem, we found we lack such tools to automate this process. We need the process is human, is manual intensive, and costs our team a lot of time spent to diagnose the root causes. The second one is query transformation. We have until now we have not available check mechanism to ensure this correctness. The third pain point is automatic configuration. As due to our experience, the configuration, it is the misconfiguration pains. It is common in user side and price from cross components. How to quantitatively evaluate the impact of configuration change and get the configuration tuning are non-standing problem. The challenge in that runtime data flow and resource usage are dynamically changed and determined by the many factors, such as data property, resource usage, and so on. Your practice, we spend much time to find the users to determine which parameter is suitable for their job. Dynamic means that the models need to capture the runtime varying data flow information and resource usage for model accuracy. Another one is replay and download tools, like such tool to automate such a process.
Okay, great. Okay, thanks a lot. So we can go for the time. I think it's good to proceed with the. If you have a question for Simenta, a heuristic for probabilistic reachability to identify hard to reach statement. If you have any question for.
So I can ask a question.
Please, Gabriel.
Yeah, so I'm just curious. My understanding just from the 5-minute talk was that your focus was just on identifying these hard to reach statements. So I'm curious, do you see any downstream further applications for your method in terms of helping with automated testing or bug finding?
Yes, that's a great question. So yes, so the main purpose that we developed this technique to identify hard to reach statements is that the scenario we are considering at this point is when you are trying to do hybrid testing, you use testing like random testing or fuzzing. On the other side, you use symbol execution or concurrent execution. Now, these two different directions has different benefits and some setbacks. Like for symbol execution, it can generate the exact input that can exercise program paths, but it's not so much scalable when you have loops and recursions. On the other side, for random testing or fuzzing, you can generate lots of inputs and it keeps trying, generating. But the problem is at some point it gets stuck. Like if you have specific checks in the program, this kind of testing cannot go further. So it needs to take help from symbolic execution. Now, if I provide you Preach, you can use this beforehand and you can identify, okay, so there are some states in the program that would be hard for random testing or fuzzing to test because there are specific checks. So if you can identify those states, you can maybe beforehand use symbolic execution to go to this particular state. And then for the other states, you can try random testing. So it's like dividing the task between these concrete testing techniques and symbolic execution-based techniques. Does that answer your question?
Yes, that makes a lot of sense. Thank you.
Great. Thanks a lot. And okay, we can go. I don't know if you have any question for Boe, for Caroline. If a human can see it, so should your system. Reliability requirement for machine vision component.
Sure, I'll ask a question.
Great.
So I recognize that I tend to work on very large systems, post-testing, whereas requirements is where we get blamed for not doing the testing right. So I realize at this stage of your career, you may not have thought about the big picture of what is a complete set of requirements and how do we design tests to it. But I'd be curious to hear your thoughts on how do you begin to operationalize your research in the testing of autonomous systems, because I think that's a very important societal challenge we need to address as a community.
Right. So as for very good question. Thank you very much. So I think for machine learning specifically, it's very hard to obtain a complete set of requirements, because that's basically the reason why people start using them in the beginning. Like specifically for vision, let's say it's because we cannot formally specify what exactly we want from these vision components. That's why people turn to ML. Like, for example, if I want to write a cat-dog classifier, it's not really reasonable to specify formal requirements, which one is dog, which one is cat. So for ML, I feel like this is one of the main challenge to what you were talking about. As for how to integrate this in the system, we have already started thinking about this, but because this is really one part of the component of the system, and it also depends on how the system is designed. Like for autonomous driving car, for example, some cars only depend on machine learning. Some has other components like, like LiDAR and everything. So it's not exactly an easy task to do because it's system specific. But that's definitely one of the things we would look at in the future. So
that's very interesting. Yes, and I mean, if I could ask a quick follow-up question. So certainly, like when you have multidisciplinary systems, you need experts, domain experts from all those engineering domains. Just as by example, I recognize there's a big difference between defect discovery or vulnerability discovery and resolution in traditional software versus machine learning algorithms. We have domain-specific techniques for doing that. I guess I would ask, have you thought about, you mentioned this formal specification. What are the challenges in doing those formal specifications that because of the nature of the machine learning domain as opposed to traditional software reliability and security? Have you thought about that at all?
So actually the challenge is from the task that you want your system to perform. So specifically for vision, it's not entirely possible to do this with a traditional software, because as you can see, for example, for autonomous driving cars, if I want to know whether my car will hit a pedestrian, we need to specify what is a pedestrian, right? So for it to be able to see it, but then this really isn't a clear definition of what a pedestrian is. Is someone on the wheelchair a pedestrian? Is someone pushing a bicycle a pedestrian, etc.? So, and also like how do you define wheelchair? And this is like a recursive problem going down. So I think the challenge lies in the task itself, because for vision it's a very normal thing for humans and animals maybe to do. But when we think about how to write this down formally as code, it's not exactly immediately clear, at least to me, how you can really do this. So machine learning has started generalizing from some data for this, and they have some kind of not really the same set of specification. They're trying to learn some specification from data for this. I think that's the difference, right? Because we're trying to generalize from data rather than as traditional software, we think about what we want and then we specify those requirements. Does that answer your question?
Oh, okay, great. And if we have a question for Gabriel, so we have also the opportunity to give him one. So a neural method for test oracle generation.
Can you hear me? Can I ask a question?
Yeah, please, great, please.
I have a question for Gabriel for the TOGA paper. Yeah. So I was going to ask, so let's say I have a list of methods that I want to test, and I don't have doc strings, like you mentioned, that those are really helpful for generating oracles. So if I give you a list of methods and the program under test, how I'll be able to use your system to generate the test prefix and the oracles. I don't have anything at all. I just know the names of the functions that I want to test.
Yeah, that's a good question. And that's something we were actually thinking about when we developed this system, is that the models, because they're trained on a large corpus and they see a lot of different examples of methods and tests during training, you can actually pass as input just a method name or a method signature, for example, without the definition and the doc string. And the system's still able to generate an oracle. And it might not be as good as if you had the doc string, but it can still make a best effort attempt.
Okay, great. Can I reach out to you sometimes later to learn more, or if I have any questions or follow-ups?
Yeah, absolutely. Please feel free to reach out to us.
Okay, great. Thank you so much. Nice work, by the way.
Thank you.
Great. I don't know if you have any other very quick question. Okay. I found, also interesting this combination with EvoSuite, that you have, for example, that Gabriel, this part. So I think it was challenging, for you to this part. So this integration.
Okay. Yeah. I think. Yeah, integrating with EvoSuite was a way to just allow us to focus on the test oracle problem, but still have a system that could automatically generate a full test. So that's why we designed the system that way, so that we could have a end-to-end system that you could just run and it would be able to generate usable tests.
Okay.
So I believe this is the difference between the Atlas paper and your paper. Is that right? Because they require some existing test context.
Yes, that's correct. So the Atlas paper focused specifically on the oracle problem on its own. And we also focus on the oracle problem. So in theory, you could actually use a similar approach with the Atlas paper and integrate it into an automated test generation tool.
Okay, great. So I think we can, if there is no any other question, we can also close the session. I thank you a lot for your attention. I thanks a lot all the speaker, all the authors, and the audience for the very interesting presentation and discussion. And please, you can join this room, like the coffee room, now the other room where you can. I hope you can follow up on this discussion. So I wish you a nice evening or day, depending on the time. And please continue to enjoy ICSE. Thanks a lot.
Thank you very much.
Thank you.
Thanks.
Bye.
Bye-bye.
Thank you.
Bye-bye.
Bye.
Bye-bye.